Hey, welcome back. Did you miss me? So, couple quick things that I want to talk about that are implications to just driving the car, being safe, and helping others out, and so you're not hurting other people. Is let's look at the relationship between this velocity, your speed, how fast you're driving, your stopping distance. So we're not changing the coefficient on the road. We're not changing the weight of your car. It turns out the mass doesn't matter because if you have double the mass, you're twice as hard to stop, but you have twice the friction force. So it turns out the mass of your car doesn't matter, but that's not changing. And of course the half doesn't change. So what we're looking at is the original velocity squared is directly proportional to the stopping distance. Okay? So what does that mean? Well, what that means is that if you were to just double your velocity, what does that do to the stopping distance? 2 squared is 4 times the stopping distance. What if you were to triple your initial velocity? Well, 3 squared is 9. It takes 9 times the distance to stop. And this is how we set up our speed limit signs, by how quickly can you stop. So in your residential areas, you got to stop quick. That's why you're not allowed to drive more than 25 miles per hour, because you expect some people might be playing out in the yard, something goes bouncing down the street and they go chasing it. You have to be able to stop in a short distance. And if you're going twice the speed limit, it's not twice the distance to stop, guys. It's 4 times the distance to stop. Now, in some places, you don't have to stop very quickly, like the interstate. That's why you can drive so stinking fast there. But that's how we set up our speed limits, by how quickly, what kind of a distance do you need to be able to stop your car if something happens out of the ordinary. Okay? So, quick thing, that's a little PSA, public service announcement there, of your speed versus how fast you're driving. So, the moral of the story is, even if you speed a little bit, that doesn't increase the stopping distance by a little bit. It increases by a lot because it varies with the square of the velocity. So a little bit faster means actually a lot more in stopping distance. Okay? That's the importance of obeying the speed limit there. Alrighty. So now, the masses cancel out here, of course. The masses cancel out, and if you're solving for the v, the 2 comes over and makes it a 2 over here. That's a 2. And then you got to do the square root of that whole dealio, right? Well, that's what that is. The square root of the 2. Oops, I got the 2 on the wrong side of my sign there. 2 on the inside. 2 times your coefficient times your g times your x. So that is how you'd find the initial velocity of how fast somebody was traveling. Okay? So the police do this all the time. So what they have to do is they have to measure the coefficient at an accident, measure how long the skid marks are, and then go back and find out what the original velocity of the car was. Alright, so 2 times all that, square root button in, bam, 18.5. Woo! It's about 40 miles an hour. Okay? So if you're going 80 miles an hour, that means it's going to be 4 times the stopping distance, or a whole football field long, just to stop a bus or a car in that scenario. Okay? So it takes a long time to stop at 80 miles per hour. Alright, so wrapping it up. Potential energy, we use a U for, it's a college term, college thing. We use the university potential energy is your mass in kilograms times your gravitational field strength, while on Earth is your 9.8 newtons per kilogram, and then of course your height there. Alright, there's your kinetic energy, 1/2 mv squared. We use a K for that. There's a lot of K's in physics, and you'll find more later on in life if you take more physics, but this is a capital K for kinetic energy. So the work energy theorem is all the work done is because of resultant force over some distance causes a change in energy. It can be a change in potential energy, but this one is focusing more on the change in kinetic energy, and that's what will be our first focus. Alrighty, so there it is, guys. Is it exciting? It's not exciting for ducks. Ducks, as you probably know, hate computers. A little crazy, I know. Alright, have a good one.